At GCSE, we tend to get this very fixed idea in our heads about atoms needing full outer shells, and that can really hold us back when we look at some of the examples, particularly of covalent bonding that we see at A level. So we're going to look at some examples that don't actually fit the 8 electrons in the outer shell rule. But there are still rules, so we'll look at the rules that still apply to these compounds. And another thing to remember is that elements are not forming bonds to get a full outer shell. They're forming bonds because bonds give out energy when they form, which we do already know from the energetics topic. And processes will tend to go in the direction of giving out energy. So even if they form an unusual number of bonds, they can still form compounds in which we don't have this octet rule. So we don't always have 8 in the outer shell. So let's have a look at what we mean. Aluminium trichloride. I actually usually introduce this to my GCSE students, and it comes up quite a lot at A level because it's an example of two things. One, it's an element without a full outer shell. So aluminium is in group 3. This is potentially unusual because we think of aluminium as a metal, but when it reacts with chlorine, it actually forms a covalent molecule. So when I'm drawing it, I'm going to put the bonds in first. Aluminium only has 3 electrons, so it can only form 3 bonds. And I'm representing those with a dot and a cross. So the maximum number of electrons that aluminium can have in its outer shell is 6, because if it starts with 3, that is the maximum it can share. The reason, incidentally, that aluminium is forming a covalent compound here is that aluminium is quite a small element. When it forms a 3+ ion, which it would do in an ionic compound, it forms a very, very small, very positively charged ion. So it will have 13 protons in its nucleus and only 10 electrons and 2 shells of electrons. And so what basically happens is, instead of forming an ion, the electrons that would have been transferred in terms of ionic bonding to the chlorine actually get attracted back to the aluminium to the point where they're sharing. So it would be a polar covalent bond, but it is covalent. And how you would know is you'd be told in a question, probably in the context of either being told it was covalent or being told to draw its shape, in which case I know it's covalent. So I've done the 3 bonds, aluminium is finished. I have deliberately left a space there because we're going to talk about that space. But of course on the chlorine does have 8 in its outer shell because it started with 7. It shared 1 with each of the aluminium electrons. So let's have a look at that space. We call aluminium trichloride an electron deficient species because it's got an orbital there. It's got an empty area in which 2 electrons could fit. And so what I'm doing now is drawing another molecule, because it is a molecule because it's covalent, of aluminium chloride next to the first molecule. And the reason that aluminium chloride comes up, therefore, is as an example of shapes, because it's a group 3 element that forms covalent bonds. They like to use those. But it's also an example of a type of bonding known as dative covalent. So if you look at that chlorine there, it's got a pair of electrons lined up next to the aluminium, and the chlorine on the other molecule can also datively covalently bond to the aluminium on the right. So we can draw this molecule using lines instead of arrows. So we can draw a displayed formula for this molecule, which looks a little bit clearer. And you can see it contains 2 dative covalent bonds, and all of the elements actually do now obey the octet rule. This molecule is called a dimer. There's no real difference between any of these bonds once they're formed. Okay, so only in the dot and cross diagram would we be showing like 2 crosses for the chlorine to show that one of them's a dative bond and the other is not. There's no difference in the strength of a covalent bond because it's all between aluminium and chlorine, and that's going to determine the strength of the bond. Would change the shape because initially, if aluminium just had the 3 chlorines, it would be a trigonal planar molecule, but when it's got 4, both of those aluminiums would arrange themselves tetrahedrally instead. So that is a genuine molecule. Those 2 molecules are joined together in what we call a dimer, 2 molecules. So sulfur. Sulfur is another example where frequently it does not contain 8 electrons in its outer shell. We're going to look at 3 examples of sulfur compounds and where they might come up, in what sort of context, and how we're not necessarily going to draw the dot and cross diagrams for all of them, but we are going to look at how sulfur could share quite a variable amount of electrons. So one thing I have not included here is sulfur behaving like oxygen. Oxygen is in group 6 as well. Oxygen can only share 2 electrons when it forms covalent bonds, and we'll look at the reason why sulfur can be different. So of course sulfur also has the capacity to share 2 electrons. So if you took, for example, at hydrogen sulfide, H2S, that's exactly the same as H2O in terms of its bonding, 2 single bonds to hydrogen atoms. However, these molecules are going to be a little bit different. So SO2, very common molecule. Oxygen needs to form 2 bonds each. That is not something that we can change. If it formed 1, it would end up with an odd number, so we can't have that. If it formed more than 2, it would have more than 8, and oxygen can't do that. So oxygen always forms 2 covalent bonds. I've drawn them as double bonds, therefore, in the middle, and what you will notice is that the sulfur has a lone pair of electrons left over. So if I just drew the double bonds in and then didn't go back and count how many electrons sulfur has, then I would maybe think that sulfur dioxide was the same shape as carbon dioxide. This is a question that you're going to be frequently asked. Why they're not the same shape? That also impacts their intermolecular forces, because one is polar and one is not. So sulfur dioxide forms 2 double bonds to oxygen, at which point we've used 4 of sulfur's electrons, so sulfur being dots. That sulfur is in group 6, so once it's used 4 of its electrons to make 2 double bonds, it has 2 left over, so it has a lone pair, so it's going to be a V-shaped molecule, and therefore that has a dipole and has stronger intermolecular forces than carbon dioxide. Once carbon has formed 2 double bonds, it has no lone pairs left over, and so that would be a linear molecule. And altogether, sulfur, if we have a little count, has 10 electrons in its outer shell. So it's used 4 in bonding of its original 6, gaining 4, and then 2 left over. Okay, what about the middle molecule then? So SF6 is used all the time in shapes of molecules, which is why I'm just going to go straight to drawing it as a displayed formula showing the shape, which is octahedral, because there are 6 fluorines bonded to the sulfur, and that is the maximum number of bonds that sulfur can make. So octahedral arrangement, 4 around the middle with 90 degrees apart, and then the 2 above and below 180 degrees apart. And there are no lone pairs because sulfur has 6 electrons. It shares 1 with each fluorine, giving the fluorine full outer shell. So my sulfur now has 12 electrons in its outer shell. Seems like rather a lot, and it is the maximum that sulfur can have. So sulfur can't have more than double the number of its group, and neither can any other element. And when we look at oxidation numbers later in the week, that is also the maximum positive oxidation number it can have. It's unlikely that you would have to draw that as a dot and cross diagram. It gets pretty crowded when you do. So 12 electrons in its outer shell. How is it doing this when we've been told that 8 is kind of the maximum? Well, we were told that 8 was the maximum at GCSE. And at GCSE, we did not go further in the periodic table than calcium, and we didn't know about the third shell. So we never went beyond 3s2. Really? Oh no, we did, sorry, went to 4s2. But what we didn't talk about was the 3D subshell. So in the first shell, we have just S. The second shell, we have S and P, making 8, 2 plus 6. In a third shell, we have S orbitals, P orbitals, and D orbitals, meaning a total of up to 18. And so it's only elements that are in the third period or below that have space for all of these extra electrons. But they can still only share electrons, they can only share as much as they have. So really the maximum for sulfur is to share 6 electrons and make 12. And this is also what it does in H2SO4, a very common molecule that we know about. And you can see, again, unlikely you would have to draw a dot and cross diagram for that. But what we have there is all of our oxygens doing exactly what oxygen always does, forming 2 bonds, either a double bond to the sulfur or a single to the sulfur and 1 to the hydrogen. And that's going to be useful when we look at how to draw the structure of a sulfate ion, which we are going to do by dot and cross diagrams. So there's several examples of molecules that do not have a full outer shell, or they have a more than full outer shell. But hopefully something you have noticed is we don't have odd numbers, because odd numbers mean radicals. Radicals are extremely reactive. They're not going to be found really in a common compound such as SO2 or H2SO4. So every time my electrons are always in pairs. 2, 4, 6, 8, 10, 12. These are all fine numbers of electrons to have in the outer shell, so long as you're checking where they are on the periodic table.